wave equation. This, as it stands here, this is the wave equation for a massive scalar field where mass is m by r, and in a 4-dimensional, in 4 dimensions. Okay, and if we consider, let us say, the Fourier moves phi 0, phi 1, phi 2, phi m, then what happens? The low energy observer is able to see only phi 0. Low energy observer would see only 0 frequency mode or 0 mode, phi 0. So, you see, when if you want to observe so-called higher modes for m greater than 0, 1, 2, 3, okay, then in order to detect, there would be a infinite number of there would exist an infinite number of massive modes, m equal to 1, 2, 3, 4, 5, and so on. And in order to prove them, you have to prove theory for 1 by r at the scales of the order of 1 by r. If you prove the theory for the scales of the order of 1 by r, then you can observe these massive modes. Okay, and the low energy observer would see only phi 0 and not other states. So in a way, for the low energy observer, this circle of radius r is not visible. Okay, this was the idea, and in particular, if you define the momentum quantum mechanically minus iota del phi, then this is minus apply P phi on phi. This is this, and this is equal to phi. This is m by r into phi. So P5 here is the momentum along the fifth direction. P5 is the quantum mechanical operator, the way you define the momentum associated with x5. Okay, the canonically conjugate of x5 is P5, is minus iota del phi, and this gives you P5, phi is m by r times this. So what we deduce here is that the mode phi m carries a momentum m by r. What we deduce out of this is that the mode phi m carries the momentum m by r. And in order to observe the states for higher m, we need to prove this theory for the scales of the order of scales of the order of 1 by r.
Yes. So that's phi m. It's not capital phi then. Or,
This one?
yeah.
Okay. Yes. Sure. Oh. Okay. This phi m. Okay. Good. So thank you. Thank you, Matthias, once again for this nice correction. And here, I don't want to discuss more on this, and we assume what we have learned from this, mainly we carry with us the idea of the compactification. Of course, here it was not possible to identify the original idea or the motivation that Kaluza-Klein had was to consider a unification of gravity at the U1 gas field, but this could not be interpreted as the correct U1 gas field, which we understand now. So that way it was not successful, but this idea of compactification, you see, was to be used much later in string theory. We have many extra dimensions, and so let us now go into what we do with our string theory. Here, for the superstring theory, we will have D equal to 10-dimensional theory, and we will have 6 extra dimensions. So eventually we compactify them into a tiny circle of the order of the size would be 10 to the power minus 33 centimeters, or of the length scales, Planckian length scale. Okay, so it's a tiny ball. And again, the low energy observers would not see it, like if we consider a long electrical cable or wire and some fly is sitting on it, we don't see it from a distance. Okay, if you zoom it, and then you can see. Okay, so this is somehow the extra dimensions can be compactified and into a tiny space. And there are many methods, we will not go into that. But now let us come back to this point where we left, corrected by Matthews, is our Virasoro constraints and Virasoro operators and algebra. And just to remind that this was T plus plus, and this was del plus x mu whole square. This was ls square summation over m and ln e to the power minus im sigma plus, and 0 equal to t minus minus is del minus x mu whole square is lm bar where Lm is your 1/2 sigma n m minus n alpha n, and Lm bar is summation over n beta m minus n beta n. So we are assuming that we are taking a scalar product in the new dimensional space-time. Okay, so and these are okay. So this Lm and Lm bar are clearly the Fourier modes of these constants. Okay, and I would not repeat many of the things that we have done before, but I would quickly come to let us say L0. We remember that when we have open string theory, we have only Lm and only alphas. When we have both the theory, when we have a closed string theory, we have alphas as well as betas, and we have Lm as well as Lm bar. Okay, because we have seen the relationship between alphas and betas. Okay, in closed string theory they stay separately. In the open string theory they get related. Once alpha is exactly equal to beta, once alpha is equal to minus of beta. Correct? With different boundary conditions and so on. So L0 is let us just consider L0 for n, and this is equal to 1/2 alpha 0 square plus 1/2, and here n or equal to 0 and equal to minus infinity to plus infinity. Okay, everything summation over all of them. N equal to minus infinity up to -1, 0, then 1 up to plus infinity. Okay, and so I am separating them out. So alpha 0 square plus this alpha minus n, alpha n plus 1/2 n equal to 1 to infinity, and alpha n alpha minus n. Okay, here yes. So and then I could write this part h equals to 1/2 of n equal to 1 to infinity alpha minus n alpha n plus 1/2 summation over mu equal to 0 to d minus 1 eta mu